We're going to talk about spin 1/2 systems, and in doing so, we're going to assume that for the time being we're only interested in this property, the spin of the system, or the particle, I should say. And also note that since we're talking about the intrinsic angular momentum, or spin, that we're going to replace our L's with S's a lot of the time from the previous equations, but we're going to assume that the operator algebra remains the same. So, our M ranges between, instead of little l, between negative s and s. In our case, s is equal to 1/2. So negative 1/2 between, M is between negative 1/2 and 1/2. But it can only go in integer steps. And there's only one integer step between negative 1/2 and positive 1/2. So M is equal to negative 1/2, or M equals positive 1/2. In that case, that means that our SZ eigenvalues can either be, since h bar is equal to that, can either be negative h bar over 2, or SZ can be positive h bar over 2. We're going to call this eigenstate spin down, and it corresponds to this state D. And we're going to call the state with positive h bar over 2 spin up, with the corresponding state U. Wonder where I got that from. In other words, as Z acts on D, and you get negative h bar over 2 D, and as Z acts on U, and you get plus h bar over 2 acting on U. Then we can see that U and D are eigenstates of a Hermitian operator, SZ. And as such, we assume that they form a basis, and that any state psi can be built with, any arbitrary state psi can be built with them. In this case, there's only two vectors in our basis, so our Hilbert space of states is said to be two-dimensional, and hence our vectors 2D. Well, we're going to pick arbitrarily the orthonormal basis, such that spin up is considered 1, 0, and spin down is considered 0, 1. And then, an arbitrary state is just A and B. This is called a spinner. Then, it's only natural that our Hermitian operators, SZ and XY and SX, should be replaced by 2 by 2 Hermitian matrices, such that, you have a linear transformation. So in our case, we're going to look at SZ. SZ is a 2 by 2 Hermitian matrix. A, B, C, D. And what makes it Hermitian is that it's equal to its Hermitian conjugate. So, which means you take the complex conjugate and you transpose it. So, in this case, since it's 2 by 2, that's fairly simple. You just swap B and C and then take the Hermitian conjugate. Or the complex conjugate, my bad. So, it must be equal to well, this means that A equals the its own complex conjugate, which means that A is a real number, and the same for D. And that B that C must equal the complex conjugate of B. So we're going to define our SZ as A, B, B star, D. And we want it to reproduce our eigenvalue equations in the basis we've chosen. h bar over 2, no, h bar over 2, 0, and sz acting on down is 0, negative h bar over 2. So A, B, B star, D, 1, 0, we're going to look at this equation here, equals A, B star is equal to h bar over 2 and 0. So we learned that A equals h bar over 2 and B equals 0. So now when we look at the second equation over here, we can write h bar over 2, 0, 0, D, acting on 0, 1, equals 0, D equals 0, negative h bar over 2. So D must equal negative h bar over 2. So putting this together, we're going to define our SZ as h bar over 2. We can pull out that factor 1, 0, 0, negative 1. Now to derive the other matrices is a little more complicated. We know that our eigenstate spin up, or U, is our state with greatest LZ equal to positive h bar over 2, and as such, if we applied the raising operator to U, it should equal 0, as we showed in the other videos. And likewise, for our spin down state D, if you applied the lowering operator to it, it should also be 0, because D is the state with the lowest LZ eigenvalue equal, or SZ eigenvalue equal to negative h bar over 2. So there's two constraints right there. We also know that our ladder operators in general, raising and lowering, we also know that our ladder operators act as this. So when k equals positive 1, we're going to raise our down state, which is m equals negative 1/2. And s equals 1/2 because we're spin 1/2. Minus m is equal to negative 1/2, so 1/2, negative 1/2, and k equals plus 1, since we're raising. And that will just be our up state, since there's only two states. That cancels, that's just 2 over 2. And so our raising operator acting on D is just going to be h bar times U. Similarly, if we were to lower the up state to the down state, m is just 1/2 since it's the up state. And we're lowering, so k equals negative 1. And we're taking it to the down state. That's going to cancel, and that's also going to be h on D. So we now have 4 equations, or 4 constraints. And But we've defined our ladder operators as A sub k is equal to Sx plus IK/Sy. And these are Hermitian operators. So we can define S sub x equals A, B, B star, D, and S sub y is equal to P, M, M star, Q, where A and D and P and Q must all be real numbers. So now we can rewrite our raising and lowering operators, our ladder operators, as A plus the raising operator is equal to A plus IP, B plus IM, B star plus IM star, D plus IQ, and our lowering operator as the same but with I flipped, A minus IP, B minus IM, B star plus IM star, and B star minus IM star, my bad, and D minus IQ. So we're going to look at the first equation. And since we defined state U is equal to 1, 0, our equation now reads this, which is equal to A plus IP and B star plus IM star. And these must be equal. So that means that A is equal to negative IP. But because the original matrices these came from are Hermitian, A and P must be real. So let's take the conjugate of this, equals IP star equals A equals IP. But A equals negative IP, so therefore P must be 0, and by consequence A equals P equals 0. And the second part of this, B star equals negative IM star, take the conjugate of that, equals IM. So we know that M is equal to negative IB, and B star is equal to negative IM star. So we can rewrite our matrices, our ladder operators, as A plus equals P, and A and P are 0, so that first term is 0. And B is equal to IM, so that's just 2B. And B star is equal to negative IM star, so the sum is 0. And D plus IQ, and our lowering operator is equal to, similarly, 0. B star minus M star, IM star, so that's just going to be 2B star, 0, and D minus IQ. Because that goes to B minus IM, which B is equal to IM, so that's just 0. So now we're going to look at the second equation with this in mind. The lowering operator acting on down is equal to 0. And we get 0, 0, 2B star, D minus IQ, acts on 0, 1, and you'll get 0, 0. That's just equal to 0 D minus IQ. Now we only get one constraint here, and that's that D equals IQ. But D and Q are real numbers by the same argument with A and P, so therefore D and Q must be 0. So now we can further write our ladder operators as A star equals 0 to B, 0 has 0, and we can write A minus as 0, 0, 2B, and star, and 0. Now let's look at the third equation. A star acting on down is equal to H bar times up. Zero, two B, and 0 equals H bar 1, 0. That must mean that B is equal to H bar over 2, and that seems to have solved our system. We don't need that last equation, but just to be safe, let's check it, make sure this is all consistent. Oops. Equals, let's see, and that is in fact consistent because it requires that B is a real number and is equal to H bar over 2. So now we can write our spin matrices. We can rewrite them. Oops. We define S x equals A, B, B star, and D. Well, we determine that A and D are 0 and that B is H bar over 2. So that's just H bar over 2. We can pull that factor out. 0, 1, 1, 0. And we determine that M is equal to negative IB. So when we write SY, it's equal to PM M star Q. We determined that P and Q were 0. And M is now negative I times B, and B is H bar over 2, so M must be negative I H bar over 2, meaning that M star is equal to I H bar over 2. So we can pull out the factor of H bar over 2, 0, negative I 0. And of course we determined that S sub Z, or we kind of defined that S sub Z equals 1, 0, 0, 1. To write it all together, Sx equals H over 2, 0, 1, 1, 0. Sy equals H bar over 2, 0, negative I 0. And Sz equals H bar over 2, 1, 0, 0, 1. These are our Pauli spin matrices, and they describe, in this particular basis, the spin angular momentum of a spin 1/2 particle in each direction, the x direction, the y direction, and the z direction. And I'm not going to do it today because of time constraints, but if you do the matrix multiplication, you can find that these actually do in fact satisfy the commutation relations, such as Sx with S of y equals I H bar Sz. And you can also show that these S of x and S of y also has eigenvalues of positive or negative H bar over 2, which reaffirms that our singling out of Sz wasn't special, and that no direction is particularly preferred. It's just under this particular basis. So these are our spin 1/2 Pauli spin matrices, and I might later make a video on the spin 1. But it's kind of tedious and time consuming. So, but it uses the same method. So, there we go.